Okay, we're going to continue our super awesome discussion on transport, getting things inside and outside of the cell, by next talking about osmosis. Oops, why was it green? Osmosis. Now, most of the time in textbooks, osmosis is defined as the facilitated, it is mostly defined as the diffusion of water. And that's how it is. Okay, so the textbook is the diffusion of water. Now, okay, it's not exactly 100% false, but it's not 100% right. Okay, I will accept that it is the passive movement of water. It is the passive movement of water. However, it is the movement of water across a membrane. Okay, across the membrane. Now, when we deal with diffusion, we are dealing with the movement of solutes. Okay, so like the salt example, and we'll use the salt example because it involves water as well. So when you drop sodium chloride, inside of just pure water, pure distilled water, okay, it will dissolve. Okay, the thing to note about that, it's not the water that is changing. It's the salt that is actually being diffused. Okay, the salt molecules are being diffused. Osmosis does involve solutes, and it does include a solvent. However, the solutes aren't what moves. Okay, it's the solute that moves. And so the way that we're going to do this, and so before we do this, you just have to think about it a little bit differently. Now, the problem a lot of people have when they talk about osmosis is they think about the water in terms of concentration. I don't want you to think about water in terms of concentration here. I want you to think about water in terms of pressure. Now, if I would have to define osmosis, here's how I would do it. The pressure, the movement of water due to pressure changes. That's how I would define it. The movement of water due to pressure change. Okay, that's how I would define osmosis. So we're going to start out here. We're going to have a container. Okay, we're going to have a container. Now, inside of this container, we are going to have this membrane. We're going to have a membrane or a barrier. And we're going to label one side of this side A, and we're going to label one side of this side B. And what we're going to do is we're going to take this and we're going to fill it with some water. Okay, so there's water in there. Okay, now this membrane, it will allow water to pass. So H2O can pass. Nothing else can. Okay, all right. So now if I have a membrane that allows water to flow through it, what's actually happening here is that water is moving in this direction and water is also moving in this direction. Okay, the water is freely flowing from one side to the other. Okay, because remember, molecules are always in motion. So you have some water molecules that are zigzagging along and going in this direction, and you have some water molecules that are zigzagging along and going in this direction. But the movement of water molecules from A to B and from B to A, from side A to B and from side B to A, have equalized out. So it's an equilibrium. Therefore, we have the volume of water in side A and the volume of water in side B are the same. Okay, we've got that out of the way. So now the next thing we actually need to start looking at when we look at this is, don't think about it in terms of water molecules. Okay, what we want to start looking at it is in terms of water pressure. Okay, when you pour water into a cup, that water is exerting a pressure on the sides of that cup and on the bottom of that cup. Okay, so this water has a pressure that is being, I don't want to do that in black. This water has a pressure that is being exerted in this direction, and this water is having a pressure that is being exerted in this direction. Okay, now what pressure is pressure equals a force over an area. Okay, so that's what pressure is. So what you have to imagine here is the individual water molecules are striking. I don't want to do it in black. Make sure I change to blue. The water molecules are striking this membrane over an area, over this little area right here, and that's causing a pressure in that amount of area. Okay, and the same side on this one, the pressure on this side, it is striking, the water molecules are striking that side of the membrane with a certain amount of a force giving us a pressure. And since we have the same amount of water molecules inside A and the same amount of water molecules inside B, the pressures are canceling each other out. So we get what's called a net movement of zero water. So some of the molecules are escaping over to this side again, some of the water is escaping over to this side again, but they are so equal, they're equalized out, that the pressures remain the same. So if I have two water molecules that just happen to flow to this side, and I have two water molecules, so if I have two water molecules that go from A to B, and then I have two water molecules that go from B to A, right? The pressures on side A and the pressure on side B is the same. Okay? So that's it. That is in pure water, separated by a membrane that allows water to go through. All right. So now what we're going to do is we're going to screw with this. Because it would be so easy if in the human body this is the way it is. But of course, no, human bodies can't be simple. We have to be freaking difficult. So what we're going to do is we're going to draw another container. We're going to put our membrane in here. And remember, this membrane is permeable to water, but nothing else. So we're going to put some water in it. Put some water right here. Water. Okay. Now, if nothing is in it, the pressure on side A is equal to side B. Okay. So we got nothing in it. Now, let's suppose, for an instance, that what I'm going to do is I'm going to put 1 mole of sodium chloride inside of side A. So I'm just dumping 6.022 times 10 to the 23rd sodium chloride compounds inside of side A. Now, remember, okay, this is an important thing. Sodium chloride cannot pass. So if when the Na and the Cl dissociate, they're just going to bounce off this membrane. They can't get through. Now, the question that I have to ask you is, what is going to happen to the pressures of water? What is going to happen to the pressures of water? Okay. Typically, what I have seen is, because people tend to think of osmosis in terms of individual molecules versus pressures, they assume that there's going to either be no change or that the pressure in A is going to increase, which is incorrect. Okay, there will be a change of pressure, 100%, and the pressure of A will not increase, because what you have to do, what you have to realize is, because sodium cannot cross this membrane, it doesn't matter. Okay, the only thing that can cross the membrane is water. Okay, so what effectively happens when you do this? When you put some sodium chloride inside A, what you have effectively done to pressure is force over area, and I should make this of water, okay, since we're dealing with water, is the force of the H2O of water. Pressure H2O of water is over the area. Okay, so let's just take, for example, that I have 10 water molecules in pure water. Let's just say I have 10 water molecules and they hit the membrane, and that's going to exert a certain amount of pressure. And on side B, I have 10 water molecules and it's going to hit the membrane, and that's going to exert a pressure. Now, what happens when I put sodium inside of side A? Okay, what happens is, instead of 10 water molecules hitting that membrane, I only have, let's say, 9 water molecules and 1 sodium molecule hitting that membrane. But does sodium matter? No. Sodium doesn't count. We're only dealing with the water. So effectively, by adding a solute to one side, I lower the water pressure. Now, if I lower the water pressure, what is going to happen is the pressure in B will effectively become greater. So that means I'm going to have a greater pressure going from this direction into A, and what that's going to do is it's going to cause side A to increase, and it's going to cause side B to decrease until the pressures are equal. Sodium chloride will still be sodium chloride on side A, and the amount I put in will always be the same. The concentration, remember, concentration is the amount over a volume, will be different. When you equalize the pressures, that's when it will change. Okay, so let's do another one. Okay, so we're gonna get these back. Now let's say I add 0.5 moles of NaCl to side B. Okay, so now, does the number matter when you're comparing it against nothing? No, whatsoever. Nothing. That number really doesn't matter. Okay, so then you just got to think, okay, so I've added some solute to side B. Side A, I have nothing. So side A's pressure stays the same. But the moment I add that moles, the pressure inside B is going to decrease. Okay, decrease. And what's going to happen? That means the water here from side A is going to move. Oops, let me do it in blue. Got to be consistent. That means the water from side A is going to move into side B. And what's going to happen is the water volume in side B is going to increase, while the water volume in side A will decrease. Again, when it will stop is when the pressure in side A and side B are equal again. And that's why we have an increase in water, because we are increasing the pressure of side B. It stops when the side B's pressure equals side A's pressure. Okay, so that's another example. So we're going to do another one. Let's get rid of our this. All right. So now let's say I've got free water here. Distilled water, free water. Pressure in A equals the pressure on B, because we've got a pretty stable fluid here. Now let's say that I put 1 mole of NaCl inside A, and I put 1 mole of NaCl inside B. Okay? So the exact same amount. I put the exact 6.0 times 6.022 times 10 to the 23rd inside A, 6.022 times 10 to the 23rd sodium chloride inside B. Does it change the pressures? Yes. Both A pressure will decrease and both B pressure will decrease. But since I put the same amount in both of them, there's going to be no change in volume. Okay? So if I have equal concentrations on both sides, osmosis is not going to occur. There's going to be no movement. There's going to be no net movement. Okay? Now, let's say that instead of putting 1 mole, oops, let me erase. Instead of putting 1 mole on one side and both sides, I put 2 moles inside A and only 1 mole inside B. Okay, so now you come to the conclusion the pressure in both of these is going to decrease. But which one is going to decrease more? Okay, and the side with more stuff dissolved in it is going to have a lower pressure. So this means that the fluid is going to move from this direction over to side A. Like this, and the water on side A is going to go up, and the water inside B is going to go down until the pressures are equalized. Okay, so this can give us a general rule. We can write a general rule for osmosis. We can say here, okay, think in terms of pressures. Of pressure. Okay, so that's 1. So star number 1. Okay, and star number 2, the side or compartment that I can put that has a higher concentration or more stuff dissolved in it will have a lower pressure. Okay, so that's the big rule. So, and if it has a lower pressure, that means water is going to flow into it. Okay, water is going to flow into it, and that is the side where the volume will increase. Okay, so now you're like, what the hell do I even care about this? Well, we'll care about this when we talk about the kidneys, because kidney sets up osmotic gradients. And we're going to care about this is because this is the reason why you can't give patients Aquafina. Okay, so now when you give somebody an IV, you give them fluids, you give them normal saline or lactated ringers or something like this, because it has to do with concentrations of the blood. Okay, now your blood concentration is about 290 milliosmoles. So blood concentration is around 290 milliosmoles. Okay, and that's just how much crap is just dissolved in your blood. Okay, pure water, if you just come to somebody pure water, that's really close to 0. That's really close to 0. And so you're going to have some changes in the red blood cell if you just start giving somebody fluids. So you got to take that into account. And what this brings us to is 2 terms called osmolarity, and tonicity. Okay, osmolarity and tonicity. Okay, and osmolarity, okay, the definition of that is the concentration of a solution and how it's written is particles per liter. Okay, it's the concentration of a solution in particles per liter. Okay, and then we have tonicity, and it is the state of a solution with respect to osmotic pressure. Okay, so the pressure on side A or side B, that's osmotic pressure. Okay, so now we have three types of tonicities. We have what's called isotonic, okay, which is the same. The solution does not cause flow. Okay, so the solution does not cause a flow. So there's no movement of water. If you've got something that's isotonic, there's no movement of water between what you're measuring. Then you have this thing called hypotonic. A hypotonic solution is less, okay, a hypotonic solution has less solutes and will lose water to osmosis. Okay, and then we have hypertonic, which is the exact opposite of hypotonic. Okay, it's got more solutes. Wow. And will gain water. Through osmosis, via osmosis. I just wanted to use the word via. Makes you sound highbrow. All right, so let's give an example of this. So, excuse me, I get really dry when I do this. Okay, so we're going to look at an isotonic solution. Okay, so if we have a container, okay, and we're going to call the container space A. Okay, and this is the best way to do this. And if you think about it as A and B, you'll never be wrong. And we're going to drop a red blood cell in here. Well, let's keep it real. Let's make it a red blood cell. We're going to drop a red blood cell in there. Okay, so we're going to say that this solution A, the concentration of stuff in here is 290 milliosmoles. OSM. Okay, so let's just say that's got 290 stuffs packed into this water. Okay, now we're going to say the red blood cell on the inside is 290 milliosmoles. Okay, so now is water going to move out of the red blood cell and into the fluid? And the answer is yes, of course. It's going to move out of the red blood cell, but also the fluid is going to run into the blood cell as well. So the blood cell is not going to change its shape. It's not going to change its shape. Okay, this is an isotonic solution. So when you put a red blood cell or you put anything in here and there's no change in volume of the red blood cell, the solution is called isotonic. The red blood cell is isotonic to the solution. That is isotonic. Okay, now we're going to take a look at a hypotonic. A hypotonic solution. So again, we've got to do the same thing. We've got to have our container, okay, and we're going to call it this A, and we're going to draw our red blood cell. Our red blood cell is going to fit in here, okay, like this. Now, in a hypotonic solution, if we look at the definition earlier, it's got less solutes. Now, the nice thing about this is the red blood cell is not going to change. 290 milliosmoles, okay, milliosmoles. Okay. Now, a hypotonic solution, it's got less stuff dissolved in it. That means the number has to be lower. Okay, so when we can use any number, we don't care, you know, which number it is. We just have to know it's got to be lower. So let's just say it's 100 milliosmoles. Okay, so now again, you got to think which side has less pressure. So remember, the water is side A, and here this red blood cell is side B. So both of them are side B. So, and you can, if you want to do this, you can just picture your little cup, side A and side B, and you can actually draw the numbers out. You can draw 100, and then you can draw 290, and then you can say which way is the water got to flow, which one has more stuff dissolved in it, and which one's got less pressure. So A has got less stuff dissolved in it, so it's got a higher pressure. So we're going to move from A to B. So that means the water is going to move into the cell. Let's do water in blue. I should have done water in blue in the other one, so let me fix that right quick. Okay, since the pressure in B is so much less, water is going to pretty much exclusively move into this cell. It's going to move into this cell. Okay, so again, if you draw it out, let me do this a little bit better. Okay, so if you draw it out, so here's our box, our little membrane, side A, side B. Okay, and so we said the glass is side A, that's 100, and the cell is side B, that's 290. Okay, and we already said above, if we look here at our little stars, the side or compartment that has a higher concentration or more stuff dissolved in it will have a lower pressure. So you always go from high pressure to low pressure. You always go from high to low. So that means side A has a higher pressure and it's going to move into side B. And so what that's going to do to side B is going to boom, it's going to cause this cell to increase in size to the point that it eventually goes pop and it bursts. And what that is called a lyse. It could lyse, L-Y-S-E, or lyses, which means to burst. But burst doesn't have a good burst sound, but pop does. Okay, so that is hypotonic. That is a hypotonic solution. It is a hypotonic solution. Okay, now the last one is we have a hypertonic. A hypertonic solution. And again, we're just going to do the same thing here. We're going to draw out our jar. Okay, and we're going to call this side A. And then we have to draw our blood cell, or whatever it is we're looking at. Okay, we're going to call this one B. Okay, and remember, what is the concentration of the blood cell? 290 milliosmoles. Okay, this is approximate. You know, it's not exact. It's like 290 to 300. So don't get caught up on the number. Okay, so but the red blood cell can't change. Okay, it can't change. Okay, so it's a hypertonic, which means that it's got a higher. So if you look at the definition, hypertonic means more solutes, and will gain water via osmosis. So what this means is in this water, so let's just say it's 290, let's just double it, 600 milliosmoles. So there's a ton more dissolved in here. Okay, it's got like double the stuff dissolved in it. So now, which side has more pressure and which side has less pressure? Since side A has more stuff dissolved in it, it's got a lower pressure. Side B has less stuff dissolved in it, it's got a higher pressure. Therefore, the water is going to move out of the cell. It's going to move out of the cell. And what that is going to do is it's going to cause this poor little guy to shrivel up into nothing. You're going to get this little shriveled red blood cell, and that's called crenated. It is a crenated. Okay, they shrivel and become crenated. Now, to work out the hypertonic, again, all you gotta do is, seriously, you just have to draw out this side. So you can draw out like we did before with osmosis. Here's side A. Here's side B. Okay, so side A, we know it's got 600 dissolved in it. Side B has got 290 before. Okay, and so again, we can go back up to the rule. The side or compartment that has a higher concentration or more stuff dissolved in it will have a lower pressure. So again, so which one's got more stuff dissolved in it? So water is going to move from B to A. It's going to move in this direction and then until they're equalized out. And usually, because we're dealing with such vast volumes, the cells don't make it, really. Okay, so that's osmosis. Okay, the last thing I want to talk to you about osmosis is, can you stop osmosis? Can osmosis be prevented? And how I'm going to demonstrate this out is I'm going to put a little thing here. We're going to draw a tube like this instead of a container, but we're going to still have that membrane. Here's our membrane. Okay, remember, this membrane is only permeable to water. Okay, so now we're going to put water on both sides. We're going to put water in this side, boom, 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 equal side here, boom, boom, boom. Now, I'm going to say, I want to put 100 milliosmoles. I don't want to do it like that. I want to do it the opposite direction. Okay, on one side, I'm going to put 100 milliOSM of something. It doesn't matter what. It doesn't matter what. The principle is important. Now, if you look at this, we'll call this side A, and we will call this side B. Which way is the water going to move? Which way is the water going to move? And if you go back to the rule of, the side that has the more stuff dissolved in it has a lower pressure. And we always go from an area of high pressure to an area of low pressure. So that means this water is going to want to move in this direction. And if the water moves from side A to side B, what's going to happen to side B is it's going to increase the water volume. Okay, cool. Can I stop this? Can I prevent this from happening? Can this be prevented? And the answer is 100% yes. The answer is 100% yes. Let's say that I put a little stopper right here. I put a stopper right here. And I exert a force downwards on this that equals the pressure of A. It will stop that. Okay, and that's what osmotic pressure is. Osmotic pressure is the amount of pressure needed to prevent osmosis. That's what osmotic pressure is. And one of my favorite things when I see this is, you see those frou-frou water, bottled water, and like it's done through a reverse osmosis pressure. So basically what they do is they do something like this and they just push harder. They push harder on here like this. And so it forces the fluid backwards. Yeah. And so you're just getting water. I think it's the stupidest thing I've ever seen in my entire life. When I read that, I was like, are you freaking joking me? This is retarded. Okay, so but that's what that is. So osmotic pressure. So just know osmotic pressure is the amount of pressure I have to exert. So this is an external pressure to prevent osmosis, to actually prevent osmosis from occurring. Okay? And I think this, along with the pressure problem, this is the fundamental difference between osmosis and diffusion. Okay, so I understand why people say diffusion and osmosis are pretty much the same thing. It's for simplicity's sake, so you don't have to, so you can think of one and the other equally, but they're not equally, and they're not the same. And I hope I've shown you that they're not the same. But can you stop diffusion? I mean, can you really stop it? And the answer is no. You really cannot stop diffusion, and because it's using the natural. It's not using pressure to drive it, but it's using the inherent motion of molecules in there to drive it. And another reason is because it's the solutes that are moving. It's not the solvent. Okay, so in osmosis, the solute set up an osmotic gradient. Okay, and if I can, in the form of pressure, and if I can counteract that pressure, I can actually stop osmosis. So that's what osmosis is. Now, this is something that you're going to have to keep in your head. Not like accurately, but you got to put it in the back of your brain, because osmosis, you do a lot of things in your body are osmosis bound. Okay, and when we get to those things, I'll always bring it back where osmosis works and where it doesn't work in those cases. But this is one of the fundamental fluid movers in our body, is osmosis, and how we set up our gradients. And I've already gone on too long, so I'm not going to ramble anymore, but that's it. So the next thing we're going to look at is we're going to look at active transport and co-transport systems. All right.